somewhere, very far from where you rest tonight, there is a small world wrapped in ice. It drifts in the outer reaches of our solar system, orbiting a great ringed giant, silent and patient. This little moon, no larger than the state of Arizona, holds within it one of the most extraordinary secrets the universe has ever whispered to us. And tonight, as you settle into stillness, we will journey there together, gently, slowly, through the cold and the quiet, to discover what lies beneath its frozen shell. Its name is Enceladus, a name borrowed from ancient mythology, given to a giant who once slept beneath the earth. How fitting, then, that this moon, too, conceals something vast and hidden beneath its surface. Enceladus is a place of wonder, a place that challenges everything we thought we knew about where life might exist and where oceans might flow. If you find comfort in stories like this, perhaps you might consider staying with us on this journey, subscribing to these quiet explorations so that we may share more peaceful nights of discovery together. Let us begin at the beginning, as all good stories do. Enceladus was first glimpsed by human eyes in the year 1789, discovered by the astronomer William Herschel, who peered through his telescope into the night sky and noticed a tiny point of light moving near Saturn. He could not have known then what secrets this little moon would one day reveal. To him, it was simply another distant companion of the ringed planet, unremarkable and cold. For nearly 2 centuries, Enceladus remained a mystery, a small frozen dot in the vastness of space. Astronomers knew it existed, but they knew little else. It was too far away, too small, too dim to study in detail. And so it waited, patient and still, keeping its secrets locked beneath miles of ancient ice, as if it knew that one day humanity would come looking. The first spacecraft to visit Enceladus were the Voyager probes, launched in the late 1970s. These brave little machines traveled for years through the void, carrying with them the hopes and curiosity of an entire world. When Voyager 1 flew past in 1980 and Voyager 2 followed in 1981, they sent back the first close-up images of this distant moon. And what they revealed was a world unlike any other. The images showed a surface of brilliant white ice, more reflective than almost any other body in the solar system. Enceladus gleamed like a pearl against the darkness, its surface crisscrossed with strange patterns and fractures. Scientists noticed something unusual. Parts of the surface appeared remarkably young, as if something had reshaped the ice relatively recently in geological terms. But the Voyagers could not stay to investigate. They had other worlds to visit, other mysteries to glimpse. And so, Enceladus returned to silence, holding on to its secrets for another generation. The images from Voyager were tantalizing, hinting at something extraordinary, but they raised more questions than they answered. What could be reshaping the ice on such a small, cold world? Why was the surface so young in places while ancient in others? These questions floated in the minds of scientists, like dreams half-remembered, waiting for the technology to catch up with the curiosity. Decades passed. The world changed in countless ways, but the dream of returning to Saturn and its moons never faded. Scientists and engineers worked quietly, patiently, designing a new mission that would take us back to that distant realm. They called it Cassini, named after the Italian astronomer who had studied Saturn's rings centuries before. And in 1997, this magnificent spacecraft was finally launched, beginning a 7-year journey to the ringed giant. Cassini arrived at Saturn in 2004, and it would spend the next 13 years exploring this magnificent system. It studied the rings, the atmosphere of Saturn itself, and the many moons that orbit in that distant neighborhood. But among all the wonders it discovered, nothing would prove more astonishing than what it found at little Enceladus. The small moon that had waited so patiently was finally about to reveal its greatest secret. The first close flyby of Enceladus took place in early 2005. As Cassini swept past the little moon, its instruments began detecting something unexpected. There was material in space around Enceladus, tiny particles of ice and other substances that should not have been there. At first, scientists were puzzled. Where could these particles be coming from? The answer would arrive with the next flyby, and it would change everything we thought we knew about this frozen world. In the summer of 2005, Cassini made an even closer pass, swooping down to within 112 miles of the surface. And there, captured in stunning images, was something no one had expected to see. Great plumes of material were erupting from the south polar region of Enceladus, shooting hundreds of miles into space. Geysers, fountains of ice and vapor were spraying from cracks in the frozen surface, reaching out toward the stars. This was extraordinary. This tiny moon, barely 300 miles across, was actively venting material into space. Nothing like this had ever been seen on such a small, cold world. The geysers suggested that something beneath the ice was providing heat, energy, activity. And slowly, a remarkable possibility began to emerge in the minds of scientists around the world. Could there be liquid water beneath the frozen shell of Enceladus? The idea seemed almost impossible. Enceladus orbits nearly 900 million miles from the Sun. At that distance, temperatures at the surface plunged to around 330 degrees below 0 Fahrenheit. This is a world of unimaginable cold, where the ice is harder than rock and the darkness is profound. How could liquid water possibly exist in such a place? And yet, the geysers seem to be telling us exactly that. As we gently continue our journey together, let us pause here for a moment in the quiet. Consider the strangeness of what we are contemplating, an ocean hidden beneath miles of ice, on a moon so distant that sunlight takes more than an hour to reach it. An ocean in the outer darkness, where no sunlight ever penetrates, where the cold is absolute, and yet, somehow, liquid water flows. It is a profound mystery, and we will explore it together, slowly, peacefully. To understand how this is possible, we must first understand Enceladus itself a little better. This moon is small, one of the smallest worlds in the solar system to show signs of geological activity. Its diameter is only about 314 miles, which means you could fit it comfortably within the borders of a small country. And yet, within this tiny sphere, extraordinary things are happening. The surface of Enceladus is covered in water ice, pristine and white. This ice is so reflective that Enceladus bounces back almost all the sunlight that reaches it, making it one of the brightest objects in the solar system. If you could stand on its surface and look around, you would see a landscape of blinding white, rolling plains of ice stretching to the horizon under a black sky filled with stars and the magnificent rings of Saturn overhead. But this pristine surface is not uniform. In the northern regions, the ice is old and cratered, marked by the impacts of countless meteorites over billions of years. Here, the surface tells a story of ancient stillness, of a world that has changed little since the early days of the solar system. But as we travel south, the landscape begins to change and the story becomes far more interesting. The southern polar region of Enceladus is dramatically different from the north. Here, the craters disappear, replaced by smooth, young terrain that has been reshaped relatively recently. And cutting across this region are four enormous fractures, long parallel cracks in the ice that scientists have affectionately named the tiger stripes. These features are the source of the mysterious geysers, and they hold the key to understanding what lies beneath. The tiger stripes stretch for about 80 miles each, running roughly parallel to one another across the southern polar region. They are remarkably warm compared to the surrounding ice, with temperatures reaching as high as -130 degrees Fahrenheit in some spots. While this is still bitterly cold by earthly standards, it is dramatically warmer than the surrounding terrain, which can be hundreds of degrees colder. Along these warm fractures, the geysers erupt continuously, not violently, not explosively, but steadily, persistently, sending their plumes of ice crystals and water vapor high into space. The material rises gracefully in the low gravity, some of it falling back to coat the surface with fresh snow, and some of it escaping into space entirely, where it becomes part of one of Saturn's rings. Enceladus is literally feeding the rings of its parent planet. Saturn itself deserves a moment of our attention, for it provides the stage on which Enceladus performs its quiet ballet. This magnificent planet, the second largest in our solar system, is wrapped in bands of pale gold and cream, its atmosphere swirling with storms larger than the Earth. But it is the rings that capture our imagination, those gossamer circles of ice and rock that have fascinated humans since Galileo first glimpsed them through his primitive telescope. The rings of Saturn stretch for hundreds of thousands of miles, yet they are remarkably thin, perhaps only 30 feet thick in most places. They are made primarily of water ice, chunks and particles ranging from tiny grains to pieces the size of houses, all orbiting the planet in a delicate gravitational dance. And as we have learned, Enceladus is one of the sources that feeds these rings, contributing fresh material through its tireless geysers. As we continue our gentle exploration, let us look more closely at the shell of ice that wraps around this remarkable world. This frozen outer layer is not a thin veneer, but a substantial shell, miles and miles thick in most places. Imagine a layer of ice stretching downward for perhaps 12 to 15 miles before you would reach anything different. This is a shell built over countless ages, frozen solid in the cold of outer space. But here is where the story becomes truly remarkable. This shell of ice, as thick and solid as it may seem, is not resting on rock. Beneath those miles of frozen water lies something extraordinary, a global ocean of liquid water, completely encircling the rocky core of the Moon. This is not a small pocket of water, not a lake or a sea, but a true ocean, wrapping around the entire world beneath the ice. Scientists estimate that this ocean is perhaps 6 miles deep on average, though it may be much deeper in some places. 6 miles of liquid water, entirely hidden from view, existing in perpetual darkness beneath the frozen shell. If you were to swim in this ocean, you would find yourself in a world of absolute blackness, where no ray of sunlight has ever penetrated, where the only boundaries are the ice above and the rock below. This ocean contains an enormous amount of water. Scientists believe there may be as much water in the ocean of Enceladus as in all the Great Lakes of North America combined, or perhaps even more. An entire sea hidden away on a tiny frozen moon in the outer reaches of our solar system. The thought is both humbling and wondrous, a reminder of how little we truly know about the universe that surrounds us. How do we know this ocean exists? The evidence comes from many sources, each piece adding to the picture like brushstrokes on a canvas. The geysers themselves were the first clue, suggesting that liquid water must exist somewhere beneath the surface. But proving the existence of a global ocean required more subtle observations, more patient investigation. One crucial piece of evidence came from observing how Enceladus wobbles as it orbits Saturn. Every moon experiences slight gravitational tugs from its parent planet, causing it to oscillate gently as it travels along its orbital path. By carefully measuring these wobbles using Cassini's instruments, scientists discovered something surprising. Enceladus wobbles more than it should if it were a solid body of ice and rock. The only way to explain this extra wobble is if the icy shell is somehow disconnected from the rocky core beneath. And the only reasonable explanation for such a disconnection is a layer of liquid water between them. The ice shell floats on the ocean like a frozen crust, free to slide and shift independently of the solid interior. This was powerful evidence that the ocean is truly global, extending beneath the entire surface. Further evidence came from Cassini flying directly through the geyser plumes. As the spacecraft passed through these fountains of material, its instruments analyzed what they contained. The results were remarkable. The plumes contained not just water ice, but also salts, similar to the salts found in Earth's oceans. This suggested that the water beneath the ice had been in contact with rock for a very long time, dissolving minerals and becoming salty, just like our own seas. The presence of salt in the plumes tells us something profound about the ocean below. It is not pure distilled water, but a complex chemical environment, where water and rock have interacted over millions or perhaps billions of years. This interaction is crucial, as we shall see, for the possibility of life. Minerals dissolving from rock provide the raw materials that life needs to build its structures and power its processes. But even more exciting than the salt were traces of other molecules detected in the plumes. Cassini found evidence of organic compounds, carbon-containing molecules that are the building blocks of life as we know it. These were not living things, not cells or organisms, but the chemical ingredients from which life might be constructed. Their presence in the plumes suggested that rich chemistry was occurring in the ocean below. Perhaps most significantly, Cassini detected molecular hydrogen in the plumes. This simple molecule, made of just two hydrogen atoms bonded together, might seem unremarkable at first. But its presence is extremely significant, because molecular hydrogen is produced when water reacts with certain types of rock at high temperatures. This suggested that somewhere at the bottom of the ocean, hot water was flowing over rocks, creating hydrogen gas that then rose up through the ocean and out through the geysers. This discovery pointed toward something wonderful: hydrothermal vents, places where hot water emerges from the rocky sea floor, rich in dissolved minerals and chemicals. On Earth, such vents are found in the deepest parts of our oceans, and they support extraordinary ecosystems of life that thrive without any sunlight at all. The possibility that similar vents might exist on Enceladus opened up thrilling possibilities for the search for life beyond Earth. As we move gently forward in our story, let us pause to appreciate the shell of ice itself. This frozen barrier between the ocean and space is not a simple, uniform layer. It varies in thickness across the moon, thinner near the warm South Pole where the geysers erupt, and thicker in the cold northern regions. The ice is constantly being reshaped, renewed, cracked, and refrozen in a slow geological dance. Near the South Pole, the ice may be only a few miles thick, allowing heat from below to reach the surface more easily. This is why the tiger stripes are warm and why the geysers can erupt from this region. The ice here is fractured and stressed, pulled apart by tidal forces as Enceladus orbits Saturn, creating the cracks through which the ocean water can escape into space. The ice shell is not perfectly still. It breathes, in a sense, flexing and relaxing as Enceladus moves around Saturn. When the Moon is closer to Saturn in its elliptical orbit, the gravitational pull is stronger, squeezing the ice. When it moves farther away, the grip relaxes and the ice expands slightly. This constant flexing generates friction and heat within the ice, helping to keep the ocean liquid below. This is one of the great mysteries of Enceladus. How does such a small moon maintain enough internal heat to keep an ocean liquid? The sun provides almost no warmth at this distance, and the moon itself is too small to retain much heat from its formation. And yet, the ocean persists, decade after decade, perhaps for millions or billions of years. Something must be generating heat inside this little world. The answer, scientists believe, lies in the tidal forces we just mentioned. As Enceladus orbits Saturn, it does not travel alone. Other moons, particularly the large moon Dione, exert their own gravitational influences. These interactions keep Enceladus's orbit slightly elliptical, ensuring that the tidal squeezing and stretching continues indefinitely. This constant flexing generates heat through friction, enough to maintain the ocean in its liquid state. It is a delicate balance, maintained over cosmic timescales. Too little heat, and the ocean would freeze solid. Too much, and the ice shell might melt entirely. But somehow, Enceladus has found the perfect equilibrium, maintaining a shell of ice above and an ocean of water below, connected by the geysers that spray material into space. It is a system of remarkable stability and beauty. The ice shell also protects the ocean from the harsh radiation of space. Saturn's magnetosphere is filled with energetic particles that would be harmful to any life forms near the surface. But the ice acts as a shield, absorbing this radiation and protecting the water below. In the ocean of Enceladus, any potential life would be safe from the cosmic rays that bombard the surface above. And so the ice shell of Enceladus serves many purposes. It insulates the ocean, protects it from radiation, and provides the cracks through which we can glimpse what lies beneath. It is both a barrier and a window, hiding the ocean from direct view while sending samples of that hidden sea out into space for our spacecraft to analyze. In its own quiet way, Enceladus is inviting us to discover its secrets. Let us pause for a moment to appreciate the sheer improbability of what we have discovered. A moon smaller than the state of Texas, orbiting nearly 1 billion miles from the warmth of the sun, maintaining a liquid ocean for billions of years. Every aspect of this story defies our intuitive expectations about what is possible in such a cold and distant realm, and yet nature has found a way. The ocean of Enceladus has probably existed for a very long time, perhaps for billions of years. This is significant for the possibility of life, because life on Earth took hundreds of millions of years to arise after our planet formed. If the ocean of Enceladus has been stable for billions of years, there would have been ample time for life to emerge and evolve if the conditions were right. The stability of the ocean also means that any life there would have had time to adapt and diversify. Even in the harsh conditions of the deep sea, life finds niches and opportunities. Microbes could have spread across the seafloor, colonizing the areas near hydrothermal vents, developing different metabolisms and strategies for survival. The ocean might be home to an entire biosphere, invisible to us, but thriving in the darkness. As we continue our peaceful journey through the night, let us now consider a question that puzzles many. How can liquid water exist in such profound cold? We are accustomed to water freezing at 32 degrees Fahrenheit, and the surface of Enceladus is hundreds of degrees colder than that. By all ordinary expectations, this moon should be frozen solid, ice from surface to core. And yet, the ocean flows. The key to understanding this apparent impossibility lies in recognizing that heat does not only come from the sun. On Earth, we are so accustomed to the warmth of sunlight that we sometimes forget other sources of heat exist. But deep in our own planet, far from the reach of solar rays, heat flows from the interior, warming the rocks and powering volcanoes. The same principle applies to Enceladus, where internal heat keeps the ocean liquid. We have already mentioned tidal heating, the friction generated as Enceladus is squeezed and stretched by Saturn's gravity. But to truly appreciate how this works, imagine slowly bending a piece of metal back and forth. The metal grows warm to the touch as the repeated flexing generates heat through friction. Something similar happens inside Enceladus, as the entire moon flexes slightly with each orbit around Saturn. This heat is generated not in one place, but throughout the interior of the moon, wherever rock and ice flex against each other. Some of this heat escapes to space through the ice shell, especially at the South Pole where the ice is thin. But enough heat is retained to maintain the ocean in its liquid state, a delicate thermal balance that has persisted for immense spans of time. There may be other sources of heat as well. Some scientists suggest that radioactive elements in the rocky core might contribute additional warmth, slowly decaying and releasing energy over billions of years. Others propose that chemical reactions between water and rock could generate heat. The exact balance of heating mechanisms is still being studied, but the result is clear. Enough heat exists to maintain the ocean. The ocean itself may also play a role in distributing heat. Warm water rising from the bottom could carry heat upward toward the ice shell, while cooler water sinks back down. This circulation would spread the warmth throughout the ocean, preventing any single area from becoming too hot or too cold. It is a self-regulating system, maintaining conditions that might be favorable for chemistry and perhaps for life. We should also consider pressure. The ocean of Enceladus is buried beneath miles of ice, which exerts considerable pressure on the water below. This pressure affects the freezing point of water, lowering it slightly. While this effect alone could not keep the ocean liquid at such cold temperatures, it adds to the other factors that maintain the liquid state. Every contribution matters in this delicate balance. The salts dissolved in the ocean also help. Just as salt on winter roads helps melt ice, the dissolved minerals in the ocean of Enceladus lower its freezing point. This makes it easier for the water to remain liquid at temperatures that would freeze pure water solid. The saltier the water, the colder it can get before freezing. The ocean's chemistry thus contributes to its own persistence. All of these factors work together: tidal heating, possible radioactive decay, chemical reactions, pressure, salinity, and convection. They create a system where liquid water can exist far from the sun, in one of the coldest environments imaginable. It is a testament to the ingenuity of nature, finding ways to maintain the conditions for liquid water even in the most unlikely places. This realization has profound implications for our understanding of where life might exist in the universe. For a long time, scientists focused on the habitable zone, the region around a star where temperatures are right for liquid water to exist on a planet's surface. But Enceladus shows us that liquid water can exist far beyond this zone, hidden beneath ice, warmed by internal processes rather than starlight. This means that oceans, like the one on Enceladus, might be common throughout the universe. Icy moons orbiting giant planets in distant star systems might harbor similar hidden seas, warmed by tidal forces and internal heat. The galaxy might be full of such worlds, each one a potential haven for life, even in the cold darkness far from any star. The possibilities are humbling to contemplate. Let us return our attention to the ocean of Enceladus itself. What might it be like in those dark waters? Scientists believe the ocean is probably quite dark since no sunlight can penetrate the miles of ice above. Any light would have to come from other sources, perhaps the glow of hydrothermal vents on the sea floor, or the faint flickers of bioluminescence if any life exists there. The temperature of the ocean is probably relatively uniform, perhaps around 32 to 40 degrees Fahrenheit throughout most of its volume. Near the seafloor, where hot water might emerge from vents, temperatures could be much higher. And near the bottom of the ice shell, the water would be colder, close to freezing. But overall, the ocean would be a relatively stable thermal environment. The pressure in the ocean would be considerable, though not extreme by Earth standards. At the bottom of Earth's deepest oceans, pressure reaches over 15,000 pounds per square inch. The ocean of Enceladus, being shallower, would have more modest pressures, perhaps similar to the pressure a few hundred feet below the surface of our own seas. Any life there would need to be adapted to these conditions, but they would not be impossibly harsh. The chemistry of the ocean is, perhaps, its most intriguing aspect. We know from Cassini's analysis of the plumes that the water contains salts, organic molecules, and dissolved gases, including carbon dioxide and molecular hydrogen. This is a rich chemical soup, containing many of the ingredients that life on Earth uses to build its structures and power its metabolism. The presence of molecular hydrogen is particularly exciting. On Earth, certain microorganisms called methanogens use hydrogen and carbon dioxide to produce methane and energy. They thrive in environments without oxygen, including hot springs and the deep ocean floor. If similar organisms existed on Enceladus, they could potentially use the hydrogen emerging from hydrothermal vents to power their metabolism. The seafloor of Enceladus is likely made of silicate rock, similar to the rocks that make up Earth's mantle. Where hot water interacts with this rock, minerals would dissolve and new minerals would form. This process, called serpentinization, releases hydrogen and creates conditions that are thought to be favorable for the origin and survival of life. The ocean floor of Enceladus might be a haven for such chemistry. As we drift through these thoughts together, imagine for a moment that you could descend through the ice of Enceladus, passing through miles of frozen water until you emerged into the ocean below. You would find yourself in complete darkness, surrounded by water that had never seen sunlight. Below you, the rocky floor would stretch away, perhaps dotted with glowing vents where hot water emerges from below. It would be a world of profound silence and stillness, yet not without movement. Currents would flow gently through the water, carrying warmth from the vents and nutrients from the rock. The ice ceiling above would creak and groan occasionally as it flexed with the tides, sending low rumbles through the water. It would be an alien environment, yet strangely peaceful, a hidden realm of quiet and darkness. And somewhere in that darkness, perhaps, something might be alive. Not necessarily complex life, not fish or plants or anything we might recognize, but perhaps simple organisms, microbes clinging to rocks near the vents, drawing energy from the chemicals dissolved in the water. Life that has never known sunlight, never known the world above the ice, content in its dark and quiet realm. In the quiet of this moment, let us imagine what the sea floor of Enceladus might look like. It would be a landscape of rock, perhaps covered in places by sediments drifting down from above. In some areas, the rock would be bare and dark. In others, mineral formations might rise from the seafloor, built up over millions of years by the precipitation of dissolved chemicals from the water. Near the hydrothermal vents, the seafloor would be warmer, perhaps even hot to the touch. Here, mineral chimneys might rise like towers built by the precipitation of metals and minerals from the superheated water. On Earth, such chimneys can grow to impressive heights, some reaching several stories tall. The vents of Enceladus might host similar structures, oases of warmth in the cold darkness. The water emerging from these vents would be rich in dissolved chemicals, hydrogen, methane, ammonia, and various metals and minerals. This chemical richness is what makes hydrothermal vents such promising environments for life. The chemicals provide the raw materials and energy that organisms need to survive, all without any input from the sun. Life at the vents is powered by the chemistry of the planet itself. Now let us turn our attention to those remarkable geysers that first revealed the secrets of Enceladus to us. These plumes of ice and vapor are among the most spectacular phenomena in our solar system, fountains of ocean water spraying directly into space, carrying with them samples of the hidden sea below. They are our window into the ocean, a gift from Enceladus that allows us to study its waters without ever landing on the surface. The geysers erupt from the tiger stripe fractures near the South Pole, those 4 long cracks in the ice that stretch for dozens of miles. Along these fissures, the ice shell has been pulled apart by tidal forces, creating openings through which ocean water can rise. When this water reaches the near vacuum of space, it instantly vaporizes and freezes, creating the brilliant white plumes that Cassini photographed. The plumes rise to remarkable heights, extending hundreds of miles above the surface of the Moon. In the low gravity of Enceladus, which is only about 1% of Earth's gravity, particles can travel very far before falling back. Some of the material reaches escape velocity and leaves Enceladus entirely, drifting outward to become part of Saturn's E-ring, a faint and diffuse ring that orbits far from the main ring system. It is remarkable to think that Enceladus is actively supplying material to Saturn's rings. This tiny moon, smaller than many asteroids, is feeding one of the most beautiful features in our solar system. The E-ring is composed almost entirely of ice particles from Enceladus's geysers, a constant stream of ocean water frozen and scattered into a vast ring around the giant planet. The geysers are not constant. They vary in intensity depending on where Enceladus is in its orbit. When the Moon is farther from Saturn, the tidal forces are weaker and the tiger stripes relax slightly. This causes the cracks to widen, allowing more material to escape. When Enceladus is closer to Saturn, the cracks are squeezed shut and the geyser activity decreases. The plumes breathe with the rhythm of the orbit. This orbital variation gave scientists important clues about how the geysers work. If the plumes were simply boiling water erupting from below, their intensity would not be so strongly linked to the tidal cycle. But the observed pattern suggests that the cracks themselves are the controlling factor, opening and closing with the tides and regulating the flow of material into space. The material in the plumes consists of several components. Most of it is water vapor, which freezes into tiny ice crystals almost immediately upon leaving the surface. These ice particles are very small, typically less than 1/1000th of an inch across, fine enough to float gently in space rather than falling quickly back to the surface. Mixed with the ice are traces of other substances: sodium chloride, the same salt found in Earth's oceans, silica particles that suggest hot water interactions with rock, and various organic molecules, including some quite complex ones. Each of these components tells us something about the ocean below, like messages in bottles sent up from the deep. Cassini made several daring passes directly through the plumes, allowing its instruments to sample the material firsthand. These flybys were carefully planned to minimize risk to the spacecraft while maximizing scientific return. Each passage through the plumes was like dipping a cup into the ocean from a billion miles away, collecting samples of that hidden sea for analysis. The instruments on Cassini were not specifically designed to search for life. The mission was planned before anyone knew the geysers existed, but they were capable of analyzing the composition of the plume material, detecting what molecules were present and in what quantities. The results were tantalizing, revealing a chemically rich environment that contained many of the ingredients associated with life on Earth. One of the most significant discoveries was the detection of large organic molecules in the plumes. These were not simple compounds like methane, but complex molecules with many carbon atoms, the kind of chemistry that on Earth is typically associated with biology. Their presence suggested that complex chemistry was occurring in the ocean, though whether this chemistry was biological or purely geological remained unknown. Scientists also found evidence of hydrothermal activity in the plume composition. The silica particles detected in the plumes are thought to form when hot water, at temperatures of at least 190 degrees Fahrenheit, interacts with rock on the seafloor. These particles are then carried up through the ocean and out through the geysers, tiny witnesses to the heat below. The geysers of Enceladus offer a unique opportunity for future exploration. Unlike other ocean worlds, where reaching the water requires drilling through miles of ice, Enceladus sends samples of its ocean directly into space. A future spacecraft could fly through the plumes with instruments designed specifically to search for signs of life, analyzing the chemistry of the ocean without ever landing. Such a mission has been proposed and studied by space agencies around the world. The technical challenges are significant. Reaching Saturn takes years, and designing instruments sensitive enough to detect signs of life in a brief flyby requires cutting-edge technology. But the scientific rewards would be enormous, potentially answering one of humanity's oldest questions. Are we alone in the universe? For now, we must content ourselves with the data Cassini gathered before its mission ended in 2017. In its final years, the spacecraft made increasingly close passes of Enceladus, gathering as much information as possible about this remarkable world. Each flyby added new pieces to the puzzle, new insights into the ocean below. When Cassini's mission ended, the spacecraft was deliberately plunged into Saturn's atmosphere, where it burned up completely. This was done to protect Enceladus and the other potentially habitable moons from any earthly contamination that might have been on the spacecraft. It was a sacrifice made to preserve the pristine nature of these worlds for future exploration. As we gently continue forward, let us reflect on what the geysers have taught us. They have shown us that an ocean exists beneath the ice, that this ocean contains the chemical building blocks of life, and that hydrothermal activity likely occurs on the sea floor. They have transformed Enceladus from an obscure, frozen moon into one of the most promising places to search for life beyond Earth. The geysers also remind us that the universe is full of surprises. Before Cassini arrived, no one expected to find active geological processes on such a small, cold moon. The discovery challenged our assumptions and expanded our understanding of where habitable conditions might exist. There may be many more surprises waiting for us in the outer reaches of our solar system and beyond. And so Enceladus continues to erupt, sending its frozen fountains into space day after day, year after year. The geysers have probably been active for millions of years, and they may continue for millions more. They are a constant reminder that this little moon is alive in its own way, dynamic and active, a world of hidden wonders. Perhaps someday, human eyes will witness these geysers firsthand, from a spacecraft orbiting nearby, or even from the surface of the moon itself. Perhaps our descendants will send probes to sample the ocean directly, diving through the cracks in the ice to explore the waters below. For now, we watch from afar, grateful for the glimpses that Cassini provided, and hopeful for what the future may bring. Before we continue to our most profound question, let us take a moment to appreciate the beauty of what we have witnessed. The geysers of Enceladus are not just scientific phenomena. They are works of natural art, fountains of frozen crystal spraying against the backdrop of Saturn's rings. In photographs taken by Cassini, they appear as delicate white plumes, ethereal and graceful, rising from the blue-white surface toward the stars. When the sun catches these plumes from behind, they glow with an inner light, each ice crystal becoming a tiny prism, scattering sunlight into subtle colors. It is a sight that no human eye has ever witnessed directly, yet we can imagine it clearly, a curtain of frozen diamonds rising from a world of ice, illuminated by a sun so distant that it appears as merely the brightest star in the sky. We arrive now at perhaps the most profound question of all. Could life exist in the ocean of Enceladus? This question has captivated scientists and dreamers alike, for it touches on our deepest curiosity about our place in the universe. Are we alone, or does life arise wherever conditions permit? Enceladus offers us a chance to begin answering this ancient question. To consider this question, we must first think about what life needs to exist. On Earth, all life requires three basic things: liquid water, a source of energy, and the right chemical building blocks. These are sometimes called the requirements for habitability. Wherever all three exist together, life on Earth has found a way to thrive, from the deepest ocean trenches to the hottest hot springs. Enceladus appears to satisfy all three requirements. Liquid water exists in abundance in the global ocean. Energy is provided by the hydrothermal activity on the seafloor, where hot water emerges rich in chemical potential. And the chemical building blocks, including organic molecules and the elements necessary for life, has been detected in the geyser plumes. All the ingredients seem to be present. But having the ingredients is not the same as having life. A kitchen stocked with flour, eggs, and sugar does not automatically produce a cake. Something more is needed: the right processes to bring the ingredients together in the right way. On Earth, we believe life originated through a series of complex chemical reactions that eventually produced the first self-replicating molecules. Whether similar processes could occur on Enceladus remains unknown. The hydrothermal vents on Earth's ocean floor offer an intriguing model for how life might exist on Enceladus. These vents, discovered in the late 1970s, support entire ecosystems that thrive without any sunlight. Microorganisms at the base of these ecosystems extract energy from chemicals in the vent fluids, and larger creatures feed on these microbes in turn. Some scientists believe that life on Earth may have originated at hydrothermal vents, where the right chemistry and energy were available to spark the first living processes. If this is true, then similar environments on Enceladus might also be capable of giving rise to life, or at least of supporting it if it somehow arrived there. The parallels between Earth's deep ocean and Enceladus's hidden sea are striking. If life does exist on Enceladus, it would almost certainly be microbial, simple single-celled organisms rather than complex plants or animals. The ocean has likely been isolated from any external source of life for billions of years, and the energy available from hydrothermal vents, while sufficient for microbes, would probably not support large, active creatures. Life there would be small, slow, and simple. But simple does not mean unimportant. If we discovered even the simplest microbe on Enceladus, it would be one of the most profound discoveries in human history. It would tell us that life is not unique to Earth, that the universe is capable of producing living things in more than one place. It would transform our understanding of our place in the cosmos. There is another possibility to consider, that life on Enceladus, if it exists, might be related to life on Earth. Early in the history of our solar system, impacts from asteroids and comets sent rocks flying between the planets and moons. Some of these rocks could have carried microbes from one world to another, seeding life in new locations. It is possible, though far from certain, that Earth and Enceladus share a common biological ancestry. Alternatively, life on Enceladus might have originated independently, arising from the chemistry of that world alone. If this were the case, and if we could study it, we would have a second example of life to compare with our own. We could begin to understand which features of life are universal and which are unique to Earth. It would be a window into the fundamental nature of living things. Of course, there is also the possibility that Enceladus is sterile, that despite having all the right ingredients, life has never arisen there. This would also be a significant discovery, telling us something about how difficult or rare the origin of life might be. Absence of evidence is not evidence of absence, as scientists like to say, but a thoroughly searched ocean with no life would be meaningful in its own way. The search for life on Enceladus is complicated by our limited knowledge of what to look for. All the life we know shares a common biochemistry, based on carbon, water, and specific molecules like DNA and proteins. But life elsewhere might be based on different chemistry entirely, using molecules we would not immediately recognize as biological. We might need to look for signs of life in new and unexpected ways. One approach is to look for biosignatures, chemical or physical signs that life is present. On Earth, life leaves distinctive traces in the environment, specific ratios of chemical isotopes, complex organic molecules, patterns of chemical consumption and production. If similar signatures were detected in the plumes of Enceladus, they might indicate biological activity below. Future missions to Enceladus might carry instruments designed specifically to detect such biosignatures. Mass spectrometers could analyze the exact composition of molecules in the plumes. Microscopes might search for cell-like structures in the ice particles. Chemical analyzers could look for the distinctive patterns that living processes create. Each instrument would add to our ability to detect life if it is there. Some scientists have proposed more ambitious missions that would actually enter the ocean of Enceladus. A probe could potentially melt its way through the ice shell, descending into the waters below to search for life directly. Such a mission would be extraordinarily challenging, requiring technologies that do not yet exist, but it represents the ultimate goal: to see the ocean of Enceladus with our own robotic eyes. For now, we can only wonder and wait. The question of life on Enceladus remains unanswered, hovering in the darkness like the moon itself. But the possibility is real, grounded in solid science and reasonable inference. Enceladus has everything we think life needs to exist. Whether life has actually arisen there is a question for future exploration to answer. As we ponder these possibilities together in the quiet of the night, consider what it would mean to discover life beyond Earth. It would tell us that life is not a cosmic accident, not a fluke of this one world alone. It would suggest that the universe is filled with living things, that wherever conditions allow, life finds a way. It would be a profound affirmation of our connection to the cosmos. Even if we never find life on Enceladus, the search itself is valuable. It pushes us to develop new technologies, to think more deeply about what life is and how it arises. It expands our knowledge of the solar system and our place within it. And it reminds us of the wonder and curiosity that drive us to explore, the same impulse that once led our ancestors to gaze up at the stars. Enceladus invites us to dream, to imagine worlds beyond our own that might harbor living things. It challenges our assumptions about where life can exist and how it might survive. And it offers us hope that someday, perhaps in our lifetimes, we might answer the ancient question of whether we are alone. For now, the question remains open and the search continues. Let us carry this sense of wonder with us as we continue through the night. Whether or not life exists on Enceladus, the moon itself is a marvel, a testament to the strange and beautiful possibilities of our universe. It is a world of ice and water, darkness and light, silence and eruption. It is a place of mystery, and mysteries are precious things. Before we move toward our gentle conclusion, let us take a moment to consider Enceladus in the context of its cosmic neighborhood. This little moon does not drift alone through the darkness. It is one of more than 80 moons that orbit the great ring giant Saturn, each with its own story, its own character, its own secrets. Saturn's family of moons is like a miniature solar system, diverse and wondrous. Among Saturn's moons, Titan stands out as the largest, a world bigger than the planet Mercury, wrapped in a thick orange atmosphere that hides its surface from view. Titan has its own mysteries: lakes of liquid methane, rivers that flow with hydrocarbons, and a landscape shaped by processes both familiar and strange. It too may harbor a subsurface ocean, though one quite different from the salty sea of Enceladus. And beyond Saturn, at the giant planet Jupiter, another icy moon beckons: Europa. Like Enceladus, Europa is thought to possess a global ocean beneath its frozen shell. Europa's ocean may be even larger than the one on Enceladus, perhaps containing more water than all the oceans of Earth combined. The search for life in our solar system has multiple promising destinations, each offering its own possibilities. What makes Enceladus special among these ocean worlds is its accessibility. The geysers offer us a way to sample the ocean without drilling through miles of ice. No other known world provides such a convenient window into its hidden waters. This makes Enceladus uniquely valuable for the search for life, a place where we might answer profound questions with technology we can build today. Scientists around the world continue to study the data from Cassini, extracting new insights from observations made years ago. New analysis techniques reveal details that were not visible before, adding to our understanding of this remarkable world. The story of Enceladus is still being written, one careful discovery at a time, each finding adding depth and nuance to our picture of the hidden ocean. And now, as our journey together begins to draw to a close, let us take a moment to rest in the quiet of this distant world. Enceladus drifts on through the darkness, as it has for billions of years, patient and still. Its ocean flows beneath the ice, hidden from view, keeping its secrets safe. The geysers spray their frozen fountains into space, a gentle rhythm that will continue long after we have finished listening. We have traveled far tonight, in our imaginations, if not in our bodies. We have crossed nearly 1 billion miles of space to visit a small frozen moon, explored the mysteries of its hidden ocean, and contemplated the possibility of life in its dark waters. It has been a journey of wonder and curiosity, the kind of journey that humans have always loved to take. Enceladus reminds us that the universe is full of surprises, that extraordinary things can exist in the most unexpected places. A global ocean on a tiny frozen moon, warmed by the gentle squeeze of gravity, sending samples of itself into space for us to discover. It is a story that science fiction writers might have invented, but it is real as the stars above us tonight. As you rest, perhaps you might imagine yourself drifting through that ocean, floating weightlessly in the dark waters beneath the ice. All is quiet there. All is still. The water cradles you gently, and the darkness is not frightening but peaceful, a darkness of rest and safety. Above you, miles of ice protect you from the cold of space. Below you, the warm rock offers comfort. The universe is vast beyond imagining, filled with more stars than there are grains of sand on all the beaches of Earth. And around many of those stars orbit planets and moons, each with its own story, its own secrets. Some of those worlds may harbor oceans like the one on Enceladus, hidden seas where strange chemistries unfold in the darkness, where perhaps life stirs in ways we cannot yet imagine. We are connected to all of this, to the stars and the planets and the moons. The atoms in our bodies were forged in the hearts of ancient stars, the same atoms that make up the ice of Enceladus and the water of its ocean. We are, in a very real sense, made of the same stuff as the cosmos. When we contemplate the wonders of distant worlds, we are contemplating our own origins. This is perhaps the greatest gift that science offers us, the knowledge that we belong to something larger than ourselves, that we are part of a story that stretches back to the beginning of time and forward to futures we cannot foresee. Enceladus, with its hidden ocean and erupting geysers, is a chapter in that story, a chapter we are only beginning to read. And so, as the night deepens and your thoughts begin to drift toward dreams, know that the universe continues on around you. Enceladus orbits Saturn, Saturn orbits the Sun, and the Sun travels through the galaxy on its long, slow journey. Everything moves, everything flows, everything changes, and yet there is a deep stillness at the heart of it all, a peace that underlies the motion. The questions we have explored tonight do not need answers right now. They can wait, patient as Enceladus itself, for future nights and future explorations. The mystery of life in the ocean, the secrets of the ice shell, the workings of the geysers, all of these can rest in the back of your mind, dreaming themselves while you dream of other things. Perhaps you will return to this story another night, or perhaps your dreams will take you to other places entirely. The universe has no shortage of wonders to explore, no limit to the mysteries that await. Every star in the sky is a sun, and around many of them orbit worlds we have never seen. There is enough wonder here to fill 1,000 lifetimes. For now, let the story of Enceladus settle gently into your thoughts. A small moon, far from the sun, covered in ice, hiding in ocean. Geysers spraying into space, carrying with them the chemistry of life. A world that should not exist, and yet it does, patient and beautiful in the outer darkness. A mystery wrapped in ice, waiting to be understood. The night sky is still there, above you, even if you cannot see it. The stars are shining, the planets are orbiting, and somewhere out there, Enceladus continues its slow dance around Saturn. The geysers erupt, the ocean flows, and the ice creaks gently with the rhythm of the tides. All is well in that distant place, as all is well here, in this moment of rest. You are safe here, wrapped in warmth and stillness. The vastness of space, which might seem cold and lonely, is also full of beauty and wonder. The same physics that keeps you warm tonight keeps the ocean of Enceladus liquid beneath its ice. The same chemistry that makes up your body makes up the waters of that distant sea. You are connected to it all. Let your breath slow. Let your thoughts soften. There is nothing you need to do now, nothing you need to understand or remember. The story will be here whenever you want to return to it, patient and waiting, like Enceladus itself. For now, you can simply rest, simply be, simply float in the quiet of the night. If you find yourself drifting toward sleep, that is perfectly fine. The darkness is not something to fear, but something to embrace, a space of rest and renewal. In the darkness, dreams can form, and in dreams, we sometimes touch the mysteries that waking life cannot reach. Perhaps you'll dream of ice and water, of geysers and stars, of questions and wonders yet to come. And if you are still awake, still listening, that is fine too. There is no rush, no urgency. The night is long, and there is time for everything. Time to think, time to wonder, time to simply be present in this moment. The universe will continue on its way, whether we watch it or not, and we can simply enjoy our small part in the cosmic dance. Thank you for taking this journey with us tonight to a small moon in the outer reaches of our solar system. Thank you for your curiosity, your wonder, your willingness to explore. These are precious qualities, worth nurturing and celebrating. They connect us to our ancestors who first looked up at the stars, and to our descendants who will one day walk among them. Enceladus will be there whenever you want to return. Its ocean will still be flowing, its geysers still erupting, its mysteries still waiting to be solved. And we will be here too, ready to take more journeys through the quiet wonders of the universe, whenever you feel the pull of curiosity calling you once more. The stars are shining, the ocean is flowing, the ice is dreaming, and you are here, part of it all, connected to everything that was and everything that will be. This moment is precious. This rest is deserved. This peace is yours. Let it wrap around you like the ice wraps around the ocean, protecting and nurturing, holding you safe. In the great silence of space, Enceladus continues its eternal journey. The tides rise and fall within its frozen shell. The ocean circulates in the darkness, and the geysers pulse with the rhythm of its orbit. It is a world in motion, yet somehow perfectly still, a paradox of activity and peace that mirrors the quiet of this moment as you rest. The ice dreams of the ocean. The ocean dreams of the rock, and the rock dreams of the heat that keeps everything in motion. It is a chain of connection that stretches from the core of this little moon to the surface of Saturn's rings, where particles of Enceladus's ocean drift in silent procession around the giant planet. Everything is connected. Everything flows. Perhaps, in the depths of that hidden ocean, something stirs. Perhaps microbial life clings to the warm rocks near the vents, unaware of the cosmos above, unaware that curious beings on a distant blue planet are wondering about them. Or perhaps the ocean is empty, a vast and patient sea waiting for life that may never come. Either way, the ocean flows on, indifferent to our questions. And you, resting here in the quiet, are part of this same universe. The atoms in your body were forged in stars. The water in your cells follows the same laws that govern the ocean of Enceladus. You're not separate from the cosmos, but woven into it, a brief and beautiful arrangement of matter that has somehow learned to wonder about itself. This capacity for wonder is perhaps our greatest gift. It has driven us to explore, to question, to reach beyond the boundaries of our small world toward the stars. It has led us to discover places like Enceladus, hidden oceans that no one imagined a few decades ago. And it will continue to drive us forward toward discoveries we cannot yet foresee. But for now, the time for wonder can wait. The time for exploration can wait. Right now, the only thing that matters is this moment of peace, this opportunity to rest, this chance to let go of the day and sink into the gentle embrace of sleep. The universe will still be there in the morning, patient and beautiful, waiting for you to wake. The stars are shining in the darkness, as they have for billions of years, as they will for billions more. The planets orbit their suns, the moons orbit their planets, and everywhere in the cosmos, the great dance of gravity and light continues. You are part of this dance, a brief and precious note in the symphony of existence. Let the darkness wrap around you like a warm blanket. Let the silence fill your ears like gentle music. Let your thoughts drift away like ice crystals rising from the geysers of Enceladus, floating gently upward into the endless night. There is nothing to hold on to, nothing to worry about, only the soft and simple act of being present in this moment. Somewhere far away, the geysers of Enceladus are still erupting, sending their frozen fountains into space. Somewhere far away, the ocean is still flowing in the darkness. And somewhere, right here, you are resting, breathing slowly, letting the world fade away. All is well. All is as it should be. All is at peace. Good night, gentle traveler. May your dreams be peaceful, and may you wake refreshed to a new day of wonder. The universe will be waiting for you, patient and beautiful, full of mysteries yet to discover. Until we meet again, rest well. Rest well.